So before we start lecture 9, let's look back at the previous in-class report. Lecture 7 was a review. Oh, minutes. Okay. Lecture 7 was a review of the first half. Since it was a review of the first half, I will skip the content and introduce what we did in the in-class report right away. First problem. When did the second year boom occur? Choose the most appropriate option from the following choices. If you look at the slide from lecture 1, you can see the second year boom is said to have started around the 1980s. Therefore, the correct answer is 1980s. Next problem. To make hello printed 4 times, what should you put in place of A in the code below? Since there is a range, in this code, the part below execute 8 times. So to output hello 4 times, we need to put 4. Next is problem to find the coefficient of determination. It's small, too big. Okay. If you execute code, the code below, that is determine parameters with single regression, calculate predicted values, and find the coefficient of determination, you get a value about 0.9. Next is about linear regression models. Choose the most appropriate explanation for the use of the simple least square ridge regression and loss regression. The last option is correct. Loss regression is suitable when variable selection is important. Simple least square is suitable when there is no multicollinearity, and ridge regression is suitable for data with multicollinearity. Is the correct answer. The k nearest neighbor method calculates the distance from each data point every time we make a prediction, so it is not suitable for a large scale dataset. Due to the natural of calculating distance, it depends on the distance for each explanatory variable. It is a method that uses all training data when making prediction here. It can classify nonlinear data as well, so the decision boundary is not necessarily linear. So the nearest neighbor method depends on the so the second choice is the correct answer. Next is a problem about reading the decision trees. Let's predict for a data point 5.8, 2.7, 3.9, 1.2. Uh, the second feature, so since the features are counted from 0, the second feature is 3.9. Since 3.9 is greater than for 2.45, we go to the right. The third feature is 1.2. So 1.2 is less than 1.75. So we go to the left. So future 2 is 3.9. 3.9 is less than 4.985. So we go to the left and find that it's classified as class 1. So answer is 1. The last problem asks you to use last regression with scikit-1. If you execute so this part, so this according to the code we provided, you get result like this. Since the fourth parameter it has the largest absolute value, we can predict the fourth explanatory variable is the most important for explaining the objective variable. This one is in class report for lecture 7. Next is story of lecture 8. In lecture 8, we talk about logistic regression. And as a method to implement it, we introduce a steepest descent method. First, we introduced something called the binary classification problem. When data is given, we want to create a function h uh, such that if we put xi into it, yi come out for a many data points. Using that function h, we predict the level of a new input x as hx. This is a binary classification problem. This function is called a classifier. When creating this classifier, linear regression didn't work well if we used it directly. So the idea was to create a classifier by using a sigmoid function. The sigmoid function returns values between 0 and 1. So we interpreted this as representing probability. This was the logistic regression. Uh, so data is given, and we do calculate like linear regression. So beta 0 plus beta 1 xi plus up to beta d xid. Then we put this into sigma. This gives us a value between 0 and 1. And we want to find beta 0 to beta d so that this represents the probability of yi equals 1. In other words, 1 minus sigma or corresponds to the probability that yi equals 1. To decide beta 0 to beta d, we use something called maximum likelihood estimation. When we decide beta 0 to beta d, we multiply the probability, this one, that the given data would turn out as given. We call this the likelihood function. The problem was to choose beta 0 to beta d so that this likelihood function becomes as large as possible. But this was difficult as it was, so we took the logarithm of this and multiplied my negative 1 over n, so e beta. So finding beta that minimize this kind of things was logistic regression. We want to solve this, but there is no method to solve it easily in one step. We have to choose a method that gets closer to the answer little by little. This time, we introduce the steepest descent method. The steep descent method is an algorithm that searches for the local minimum value of a function using only the gradient of the function. We decide on some location, we decide on the initial value here. So initial value. Uh, from there, we match by a gradient by alpha and subtract it to make the next location as an update. By doing this, we can make the value of f here. So the value of f here smaller than value of f here. If we repeat this, we will eventually get a local minimum value. This method is called the steepest descent method. This alpha is called the learning rate. Also, the steepest descent method is also called the gradient descent method. The steepest descent method was a method that updates the data in the steepest direction at that location. That by repeating the update in the steepest direction, it is a method that moves the data towards the valley bottom. This vector is called the gradient, and because it descends in the opposite direction of the gradient, it was called the gradient descent method. There is no guarantee that the minimum value obtained by this method is the minimum value of the whole function, and it may be local minimum, like that. There was a story that we need to choose the learning rate well. If it's too large, it might oscillate, and if it's too small, we can always get the accurate result if we have infinite time. But it may take time to converge, so we needed to choose it well. Now, to apply this to logistic regression, we need the partial derivative of this E beta. The partial derivative of beta can be written in this form. The partial derivative, when we implement the steepest descent method using this, it becomes like this form here. We decide the data first, calculate the gradient, multiply by alpha, and subtract. By repeating this, we get closer to the optimal solution. By using this, we create a function that returns 1 and 0 depending where the beta 0 plus beta 1 times xi1 plus up to beta d x times xi is greater than or equal to 0 or smaller than 0, we can create a cluster. This was a story. Okay, so let's go to let's look at the in-class report for lecture 8. Choose Okay, first problem, choose an incorrect statement from the following descriptions. In logistic regression, the least square method is used to optimize the parameter. This is false. We don't minimize the sum of squared errors, but instead aim to maximize the likelihood function. Linear regression is suitable for predicting continuous variable values and is not suitable for a binary classification problem. This is true. Uh, the sigmoid function limits the output values between 0 and 1, and we perform binary classification by interrupting this as a probability. This is also true. Maximum likelihood estimation aims to maximize the probability, that is a likelihood function, to estimate the parameters of the model based on the given data. It's also true. So the first option is incorrect choice. Next problem, the goal of steepest descent method is to reach a local or global minimum by setting an appropriate lagging rate. This is the goal and it's correct. The steepest descent method takes the approach of gradually descending the parameter space to find the parameters that minimize the cost function. This is correct. When the learning rate is very large, progress is first, but it may cause oscillation and fail to converge. So it doesn't necessarily make it easy to find. So the third option is false. Okay, the fourth option, when the learning rate is very small, the steepest descent method takes a very long time to converge, but always reaches a more accurate optimal solution. Actually, it reaches a local optimal solution. So the third option is false. Next is a problem where we actually apply data. So when we estimate parameter using logistic regression with this x and y data and output the data, we get the result like this. The output shows beta 0 or beta 1, beta 2. So choose the value closest to the coefficient of beta 1 for the first explanatory variable. So beta 1 is 3.1643, blah, blah, blah. So beta 1 is approximately 3.16. There were quite a few mistakes, but please note the indexing start from 0. So many students uh, made mistakes. Beta 2 is minus 0.4654, blah, blah, blah. Approximately is minus 47. The choice one is minus 0.46. Next is a problem about the steepest descent method. This function appears in the slide here, this function. And the graph of y equals fx draws a graph like this. Of course, you could try all patterns, but if you try all four patterns, you would get the answer. However, since we know that y equals fx becomes a graph from earlier, unless the initial value is greater than 1, we cannot reach the true global minimum on the right side. So we can predict that we must choose the fourth option, so initial value to 0. When we actually execute it, we get a result like this. So, okay, we try. Yes, here. So let's start. So the initial value is 2 and the lagging rate is 0.01. We'll set 0.0 and 0.01. Yes, we obtain the global minimum value. So we get a result like this and can confirm the minimum value is negative around minus, so negative around 20. Find, okay, next problem. Find the minimum value of the function fx to x 4 plus 4x3 plus 3x2 plus 9x plus 6 using the steepest descent method. Since we need to implement the derivative ourselves, okay, let's execute. Oh, it's no. Well, so here, okay, this part. This is fx. This is a derivative. Okay. So from there on, we can implement it like this. And we calculate, we get the result like this. So since we need to answer the minimum value, the minimum value is around minus 4.125. So answer is this second option. This concludes so in class report explanation. There were no comments that seemed to require specific response, so I would like to start the class. So among the comments, there was mention of errors occurring. When errors occur and you don't understand what's happening, feel free to ask questions. Please ask questions as needed. Okay. Today I will talk about support vector machines. This will be the final session on classification methods. What we want to do with classification is classify data. We wanted to distinguish whether animal in image is a dog or cat, or distinguish whether email text is spam or normal email. Especially, we want to map the dimensional vectors to 1 and or minus 1. Until now, in the previous session, we use 1 and 0, but this time we use -1 for convenience later. In case like this, where the red data is upper right and blue data is in the lower left, we can somehow predict the pattern. If we can draw a line like this and classify one side of the line as red, the other side as blue, it becomes easy to understand. On the other hand, in the other example, when they are mixed together like this, we cannot do such classification. Let's say, let's say we are given pairs of image and labels as data. When the exists W and V, so W and V such that this equation yi times W transpose xi plus B is greater than 0 holds for all these data. We call it linearly separable. This might not be immediately clear as it is, but specifically when yi is 1, it says that this one is 1, it says that the transpose xi plus, so that, oh, so wxi plus b uh, is greater than 0. On the other hand, when it is -1, so this is -1, it becomes so wtxi plus b is less than 0. So this is writing the case division in one equation. Here W and xi d-dimensional vectors respectively, and this is their inner product. Since it might not be immediately clear from looking at this, let's look at a specific example. This was example 5.1 area, and this is a linear separable. If we take as vector 1, 1 and b as -4, then wx plus b becomes x1 plus x2 minus 4. Specifically, for example, 3, 2 is classified as level 1 when the substitute 3, 2, so 3 plus 2 minus 4 is 1, which is greater than 0. So when the level is 1, so that is classified as red. So this being positive is correct. We have to check this for all other data. For example, it's 3, 3. The 3 plus 3 minus 4 is 2, which is greater than 0. So those labels as 1 on this side are correct. On the opposite side, if we take the point 1, 2, 1 plus 2 minus 4 is -1, which is less than 0. So when the level is -1, That is a blue point. For the other point, this is also 1 plus 1 minus 4. This is minus 2, which is less than 0. So, this is this is classified as minus 1. So this is what the equation we mentioned earlier means. In case of other examples, so example 4, 2, since they are mixed together, we cannot draw such a line, so it is not linear separable. Okay, so when we use the parameter w equals 1, 1 and b equals minus 4 from earlier, if we color the area where wx plus b is positive in red, and the area where it is negative in blue, it looks like this. In the previous session, we talked about the classifier in the resistive equation session. If we allow anything for this classifier, uh, the difficulty becomes high. So here we consider limiting to linear classifier. If we define h by sine of wx plus b, this sine function return 1 when positive and minus 1 when negative. So when we apply, so so it becomes 1 in the red part and minus 1 is the blue part. There are various ways to create this linear classifier. As long as we can separate red point and blue point with any way by drawing lines like that. Uh, so if it can separate them, we can use it to create a classifier. So there is freedom in how to decide. What we want to do with support Beckman machine this time is to have as much margin as possible between the data and the decision boundary. Okay, let's take a break. Okay, let's restart. Uh, To write it so it's specifically, the idea of support vector machine is to make the distance from data to the decision boundary as large as possible. This distance from the data to decision boundary is called the margin. The distance from xi to hyperplane wx plus b is called 0 can be written here. I think you learned about the distance from a point to a line in mathematics before, and this is a generalization of that. We calculate wxi plus b at that point, uh, and divide it by the square root of the sum of double squared. This gives us a distance. So support vector machines find W and V that satisfy for this for all Y, I. That is, if such W and V exist, it means linear separable. There are various ways to choose such W and B, but among them, support vector machines decide W and B to maximize margin. Since we want to make the margin as large as possible, this is called margin maximization. In the earlier example, the decision boundary is like this, and the closest point among them is this one. And the distance from here to the straight line is called a margin. So we want to make this as large as possible. Here, or here, or here, or here. We want to use this, but since it's difficult to handle as it is, we transform it. Let's call the smallest value among the distance at each point yi times wxi plus b as m. Since we assume the data is linearly separable, this m is positive. And the yi wxi plus b for each point is greater than 0. Even if we correct several things, hmm. Sorry, so listen, so this is so m is the minimum value. So yi w y times wxi plus b is greater than or equal to m for all I. And the minimum value m is still greater than 0, so this relationship holds. So we divided this by m. When we do this to both sides, it becomes like this. And let's call double divided m as double children, and b divided m as b children. So we obtain this inequality. So then the margin from area can be rewritten as follows. Since W is independent of I, it can be taken outside. And the minimum value part here is exactly the definition of M. So this becomes M. Uh, so it becomes M over the norm of W. This can be rewritten, so W over M norm. So this can be rewritten like this with W tilde. So which is W divided by M. So, so this margin is the same as maximizing as the reciprocal of 1 over the norm of W tilde. So maximizing the reciprocal is the same as minimizing the original number. So here and here. So the condition part, so this condition part from earlier can be written like this. So it becomes condition yi times w tilde xi plus b tilde is greater than or equal to 1. So this part. So if we write this as minimizing problem, it becomes like this. You might wonder if can be solved, but actually this is called a convex quadratical problem, program problem. And efficient optimization algorithms for solving this are known. There are various methods. For example, the primal dual interior point method. But we will not discuss details here. Anyway, it is okay to know that there are methods to find the optimal solution for this, to find W and B. If we call the optimal solution obtained this way W hat and B hat, then the classifier we were looking for can be written like this. So far, we have been introducing support vector machines, but what support vector is here? For the optimal solution, actually some xi, yi are found such that yi times wxi plus b equals 1. In the first example we gave, the decision boundary is actually the optimal solution. And in this example, 1, 2, 2, 1, 2, 3, 2, 2, 3, those points. The points closest to the decision boundary are called support vectors. In a sense, these points are supporting the decision boundary, like that. So they are called support vectors because they are vectors are support. The important thing is their points like 1, so 1, 1 and 3, 3, but these 2 points are actually irrelevant for maximizing the margin. Points other than support vectors does not contribute to the decision boundary, So no matter how many points there are far from this decision boundary, like that, the result doesn't change. In this sense, it has a property of being robust to outliers. Now we have been talking about linear separable cases so far, but let's discuss how to handle linear non-separable data. In that case, we create a classifier that can tolerate some errors. So let's do some preparation. Given data, oh, oh. Given data, a linear classifier that doesn't separate well, we define its loss as follows. When yi times wxi plus b is greater than or equal to 1, it separates well, so the loss is 0, meaning it classifies well. When yi times wxi plus b is less than 1, when defined the loss look like this. This represents how much smaller yi times wxi plus b is from 1. In other words, it can be seen as a quantity that represents how poorly it classifies. So the loss can be written together as a maximum of these two values. Uh, we consider a problem that want to minimize the loss as much as possible, while also minimize the square for the norm of W, which correspond to the square of the inverse of the margin. So we consider soft margin support vector machine. The The previous problem considered minimizing the squared part W, but we set up the problem so that the sum of the losses from earlier is also minimized. The constant C that appears here is the weight that adjusts the balance between margin and loss. If C is small, so if C is small, W becomes small, which means emphasis is placed on making the margin large. On the other hand, C becomes large, so the influence of this loss becomes large. So to make the whole thing small, we have to make this loss small. Here we call it software margin support vector machine. Support vector machine that only handle linear separable data are called hard margin support vector machines. To distinguish them from soft margin support vector machines. How do we solve this? The steepest descent method can be used for soft margin support vector machines. What was the steepest descent method? We calculate the gradient, decide the current location property, then multiply the gradient by alpha and subtract. By doing this, we can find a location that has a smaller value at a better place than the Callias value at xi. So we just needed to be able to calculate partial derivative. By the way, although we introduced the steepest descent method here, methods solve the dual problem are actually faster. So those methods, SMMO algorithm, and DCD algorithm are often used in practice, but they are a bit difficult, so we omit them here. We want to calculate partial derivatives, but the maximum function is not differentiable. However, if we decide to use either the left or right derivative at x equals 0, the steepest descent method can be handled. So, for example, for a function x equals 0, if we decide on a rule to treat the derivative at x equals 0 as 0, we can run the calculation. Let's think about the problem for soft margin support vector machines. Let's think about partial derivatives. Here, let's consider something divided by n as an empirical rule to increase stability and efficiency, making it 1 over 2n. When 1 minus here, so 1 minus yi times wxi plus b is less than 0, it becomes 0. So at the time, we decide to set the partial derivative with respect to wj at 0. When 1 minus yi times wxi plus b is greater than 0, we just need to calculate the partial derivative of this. That is the partial derivative of 1 minus yi wtxi plus b with respect to wj. When we calculate the partial derivative, strictly speaking, it's the partial derivative under the rule from earlier, but for the first part, double squared part, we can just differentiate it directly. For the partial derivatives, so this part becomes this part. For the partial derivative of the summation part, when 1 minus yi times wxi plus b is less than 1 or more, it becomes less than 1, it becomes 0. So we set it to 0 there. So we don't need to handle it there. The other part becomes minus so this part minus c yixij. So we just need to consider the summation of this only yi wxi plus b is less than 1. And this becomes a partial derivative. The partial derivative with respect to b can be done similarly. So the algorithm for the soft margin support vector machine becomes like this. Uh, uh, we decide W and B appropriately, then calculate the partial derivative W and B, so this part. For that, we first set dw, which which finally correspond to the partial derivative as dw equals w over n and db equals 0. Since we only need to calculate the partial derivative when yi times wx I plus b is less than 1, uh, so when yi times wxi plus b is less than 1, we subtract y1 from dw and subtract yi from dv. By doing this subtraction only when this condition is satisfied, we can calculate the partial derivative. Once we can calculate the partial derivative, we follow the rule of steepest descent method and multiply the partial derivative by alpha and subtract. This algorithm repeats until the update amount becomes sufficient small. Let's specifically introduce and explain step 2 in the first half of the procedure. What we want to do in the first half of the step 2 is to calculate the partial derivative. So we want to do this kind of calculation. For example, if there are only two data points, and y1 times wx1 plus b is less than 1, and y2 wx2 plus b is greater than or equal to 1, then this condition is satisfied only when I is 1. So dw of w becomes like this. For v, it becomes like this. We calculated this with a program. In the procedure, this is nicely divided. First, we set dw as w over n and db as 0. Since y1 wx1 plus b is less than 1, we subtract y1 x1 from dw and cy1, so this part is 1, uh, from db. As a result, dw becomes w minus cy1 xy1. Oh, this I forget. W over n. This part db minus equal minus cy1 x1. 3. For the the second data point, since y2 plus b is not less than 1, we do nothing. As a result, dw becomes like this. db becomes like this, giving the same result as before. When we write this with NumPy, it looks like this. Uh, so alpha is running rate, k is how many times to loop, and EPS, so epsilon is short, EPS is short for epsilon. It's a parameter to how small the weight update amount should become before we stop. Actually, this k is for loop, and the for statement in range is calculating the partial derivative. So partial derivative from earlier. Only when yiwxi plus p is less than 1, we do the process of subtracting this from dw and db. When we actually execute the calculation specifically, we get the result like this. To summarize what we have covered so far, support vector machine is a method that emphasizes maximizing the margin between classes. Therefore, it is powerful when class separation is clear. It is determined based on the data points closest to the decision boundary on both sides, that is, support vectors. So the further data point is from the decision boundary, the smaller the influence that the data point has. Therefore, it has the property of being less susceptible to outliers far from the decision boundary. With logistic regression, it is effective even if it is far from the decision boundary. Comparing with logistic regression, support vector machines determine the decision boundary by maximizing the margin, while logistic regression determines the decision boundary based on the probability that a data point belongs to specific class. So the objectives are different. The output of support vector machines is class level -1 or 1, while logistic regression outputs the probability of belonging to a class. Okay, let's take a break. Okay, let's restart. As a supplement, let me briefly introduce support vector machines for data that is not linear separable. Actually, although we will not discuss the details and will not go too deep, support vector machines can also perform nonlinear classification. We cannot distinguish classes with simple lines or planes, but in such cases, we can use nonlinear functions such as polynomial. The idea is to so this is first, this is non-linear separable. This data is not linear separable. If we divide it by this line, this is blue and red, but blue part is also here, so it's not. So it can. So it's not good. So the idea is to move the problem to higher dimension space where it is linear separable. Initially, suppose we have one dimension data with red in the center and blue on the both sides. Then this is not linear separable. But if we plot the data with respect to this x and x square, when x equals 0, x and x square at so x equals 0, this point corresponds to x 0, 0. For example, x equals -2. Uh, the data at the point x equals -2 is -2, 4. So it will be here. Then this becomes linear separable data. So by adding nonlinear functions such as polynomials, we can bring it to a linearly separable problem. In other words, the technique is to move the problem to a linear separable higher dimension space. However, if we actually calculate data in higher dimension space, the computational cost becomes very high. So by using the kernel trick, there is a known method that allows us to calculate in the original space without actually calculated data in higher dimension space. We will only introduce this topic in words and refer you to the textbook. So sorry, it's Japanese. Uh, so this concludes our discussion for support vector machines. We have introduced several classification methods so far, so let's talk about how to evaluate them. Let's say we want to know how good the method is. As a specific example, let's consider the case of diagnose. Well, so let's consider the case of diagnose disease. Even if we say the diagnosis was wrong, there were two cases diagnosed as having the disease but didn't have the disease, and diagnosed as not having the disease but had the disease. So we prepare terminology to distinguish between these. When we diagnose as having the disease and the person actually has disease, we call it true positive. When we diagnose as having the disease, but the person actually doesn't have disease, we call it false positive. In other words, when we diagnose as having the disease, we get a positive reaction. So positive. Regardless, regardless of whether the person actually has a disease or not, we get a positive result in that case. When the person actually has a disease, it was truly positive. So we call it true positive. When the person actually does not have the disease, since it was positive, we call it false positive. On the other hand, when we diagnose as not having the disease, we get a negative result. When the person truly doesn't have disease, we call it true negative. When we diagnose as not having a disease, but the person actually has a disease, we call it false negative. I think the metric you often use is accuracy. For accuracy, let's call the number of true positive TP, the number of false positive FP. Uh, so let's call the number of true positive TP. The true negative is FP, the false positive FP, the false negative FN. In that case, the total number of data point is sum of these four. So we divide by the number of correct predictions. Now, the number of correct prediction is people who are truly positive and people who are truly negative. So it becomes TP plus TN. This is accuracy. This is commonly used, generally well used, and natural. So it is easy to understand. But for example, when half of the people actually have the disease and the other half do not, even if we diagnose all people as not having the disease, when we calculate this, it becomes 0.5, which means 50% accuracy. Real data has bias. For a rare disease, almost everyone doesn't have the disease. So even if we diagnose everyone as not having the disease, the accuracy becomes very high. So whether it is a machine learning method or anything else, even if there is a good method, whether it has the ability to discriminate or not, both can produce good numbers. So accuracy alone doesn't work well. So there are two concepts. There are precision and recall. First, precision represents how many how many of the diagnose, so here, so how many of those diagnosed as having the disease actually had the disease? So it is TP or TP plus FP, which represent how many were truly positive among those judged as positive. This is precision. So if this number is high, there is a high possibility that the people diagnosed as having the disease actually have the disease. On the other hand, since this does not consider false negatives, there is uh, there is possibility of missing people who actually have the disease. Even if precision is high, there is another concept called recall. So this part. This is how many people who actually had the disease could be diagnosed as having the disease, which is TP over TP plus FN. So this is the proportion judged as positive among people who actually had the disease. So if this number is high, it means that there are few people who actually have the disease but miss it. On the other hand, since false positive not included in this calculation, even if this recall is high, there is a possibility of many false positives. So there is a possibility of diagnosing people who don't actually have the disease as having the disease. Whew. So there is generally a trade-off relationship between yes. So there is generally trade-off relationship between them. So we want to make both high, but generally that doesn't work well. Moreover, there is a question of whether we need to make both high in the first place. For example, if we want to accurate predictions, even if there are many misses, we focus on precision. For example, it is better to let some spam slip through than to have important emails classified as spam. So when we want to block only what we know for sure is spam, we should focus on precision. On the other hand, when we want to reduce omissions, even if there are some errors, we focus on recall. For example, even if there are misdiagnosed, we can re-examine. So although the proportion that becomes positive might be high, even if we mistakes, if we test again right away, the possibility of actually having the disease increases. So when we don't want to miss people who have the disease, recall becomes important. Even so, there are cases we want to balance both. So in such cases, uh, what is often used to compare classification model is F-score, which is a harmonic mean of precision and recall. It is known that if precision and recall are good, the F-score becomes large. The harmonic mean is when we take the reciprocal and them and divide by 2. When we calculate this, it becomes like this. Mhm. When examining precision recall and F-score, we cannot use the data that was used to determine the model parameters. In the end, we examine precision recall and F-score for result of applying the model to test data. This was a story about precision recall and F-score, which are one of evaluation methods for classification methods. Now let's move on to the discussion about code. Now let's talk about the implementation. First, as usual, we start with preparing with the libraries. Uh, since hard margin support vector machine are a bit complicated, we will work on the implementation of soft margin support vector machines. As we discussed in class, this uses steepest descent method. Actually, it would be better to use SMO algorithm or DCD algorithm. That solves the dual problem, but this is the most understandable method among the methods we covered in this class, we use the steepest descent method. First, we initialize W and B, mm, so bias to 0. Then we calculate dW, which is a gradient, and dB, which is a partial derivative with respect to B. From here, from here to here, no, here is the part of that calculates the gradient. Since we can calculate the gradient, we multiply by alpha and subtract to get beta W and beta V. When the update amount when the update amount of weights becomes small, we consider it converged and end the loop. If the update amount is not yet small, we replace W and B with the W and B calculated uh, and obtained earlier, and repeat the calculation again. Uh, we create a function like to make two-dimensional data. This separation specifies how much to, so this one. This separation specifies how much to separate them. For those who are curious, please take a look, but just think that we are creating some data. Uh, when data is given, we train the support vector machines parameters and outputs weights and bias. The calculation can actually be done like this. For this, when we actually output it, data are like this, comes out. We draw the decision boundary and run from this form. Uh, by the way, so since the distance between the scattered data here and the center part in the scatter plot here is specified by separation, we can adjust it with that. So if we change here, so we change separation for, so distance is bigger. So I change again. Okay, let's back. The classifier can actually be created like this as well. The data we used for training earlier was executed with separation equals to 0.0 and seed equals 1. So indeed here, so separation is 2 and seed is 1. With the same separation distance we set to seed to 3. That is, we generate data using different random numbers. In other words, the way of creating the underlying data doesn't change, but the random numbers are changing. By using this, let's create test data. Then we make prediction on the test data and calculate the number of true positive, false positive, true negative, false negative. Uh, so this part is correspond to here. So this part returns true when y predict that is the predict label also here. So y predict so this part return true when that is predict label is 1 and returns false otherwise. On the other hand, Uh, this side becomes true when the actually y test is 1 and becomes false otherwise. Since we are taking and logical conjunction of these, it becomes true when the accurate actual value is 1 and the predicted value is 1, and becomes false otherwise. When so we generated 50 data points earlier, and the first data point has both actually predict values of 1. When either 1 is minus 1 or when either 1 is minus 1 or both are minus 1, it becomes false, like that. This can be written like so. So this can be written like this. Since true correspond to 1, uh, so true correspond to 1, false correspond to 0. We can calculate the number of true positive by calculating the sum of these. So this is number of cases where it was positive, but so this one. So this number of cases where it was positive, but the actual data was not. That is, it was wrong. So this is number of false positive. When the predict value was negative, minus 1, but it actually was minus 1. This is number of true negative. And this is when the prediction was minus 1, that is predicted as negative, but it was not. So we can calculate the number of false negative. Then we calculate recall, precision, F-score respectively, and we get a result like this. So in this case, we obtain results with high precision. In this way, we can calculate the recall precision and F-score for data. The following is code for creating slides. That's all.